NASA Edge returns to NASA Goddard to monitor the progress of the Magnetospheric Multi-scale Mission. We go inside the clean room to get a closer look at how this highly maneuverable set of satellites is powered. It's part propulsion, part co-host, and part 2 MMS.
Somebody must have lost a bet for us to get access in here. We got to be careful.
Watch your step.
Oh yeah, good point. And the other thing is, this is a unique opportunity to see the guts of MMS.
Especially because they're installing parts of the propulsion system.
Yeah, so we better be careful.
Hey, no looking for stowaway space.
Man, I can't make any guarantees.
All right, man, go for it.
Eric, we often talk about satellites in terms of the instruments that we put on them, but this is a unique case. We're getting the chance to take a look at MMS at the very early stages, and now we're seeing the propulsion system. What goes into deciding on a propulsion system for a new satellite?
Well, we are seeing it in an early phase of the build, but prior to this, several years before this, we actually made conscious decisions about what kind of system we wanted to fly on MMS. The kinds of systems that we considered included solid propellants, bipropellants, cold gas systems, electric propulsion, and of course the one that we're flying on MMS, a monopropellant system.
Now, is that a common system for satellites?
It is a very common propellant system for satellites. It's based on hydrazine as the propellant, and what we do is we decompose the hydrazine as it's coming out of a thruster to produce hot gas, which gives us the thrust that we need from our propulsion system.
Each of the 4 spacecraft are actually spinners. So they're rotating at about 3 RPM, and we have 2 different types of thrusters that will allow that to happen. So we have these thrusters that stick straight out. We call these radial thrusters. And then we have these thrusters over here, which are called axial thrusters. These radial thrusters will be the ones that will help keep the spacecraft spinning and get it to go to where we need it to go. If you think of a top, whenever you have a top spinning, once it's about to fall, it starts wobbling. And a similar thing happens with these spacecraft. Every so often, it'll wobble. It's called nutation. So these axial thrusters will help to prevent a lot of that nutation.
Now, that spinning of the spacecraft, that's actually very important for keeping them moving as well, right?
It is critical to the scientific measurements that we want to do on the spacecraft. MMS has a significant number of deployable booms, both rigid booms as well as wire booms, and we also have booms that stick out the top and bottom of the spacecraft. It is critical to the spin of the spacecraft to maintain a constant spin so that all those booms remain bound to within where they're supposed to be moving.
So they can get the right data at the right time.
Exactly, and also so that we know where they are, so that the scientists know where they're getting their measurements from.
And the propulsion system can help adjust that if it is moving out of place.
Absolutely, and we will be doing that. Anytime we fire the propulsion system, we'll be introducing disturbances into the system, which we'll have to correct as well. So we are actually the main disturbance as well as what helps us to get anywhere.
How will they operate as far as orienting the observatories in their formation?
So the radial thrusters will be doing the majority of the work in getting each spacecraft. These thrusters will be pulsed. If we need the spacecraft to go here, and because this thing is spinning, the thrusters will have to pulse over a 20-second time frame, and the pulse width, or the time that these thrusters are pulsing, will depend on what's needed to get the spacecraft to where it needs to go.
And when you say pulse, you mean pss, pss,
yep,
like that?
Yep, just like that.
How long do you expect that propulsion system to work for MMS?
It depends very much on how often we have to adjust the maneuvers. There are a number of operational considerations that have to go into that. Mainly, we have to decide how dynamically we want to fly the constellation. What we expect from the 4 spacecraft is that there's actually going to be a wide range of propellant left on board. A very similar mission that we flew recently was Themis. Themis, as you may know, took 2 of their spacecraft from a very similar orbit and actually sent 2 of those spacecraft off to orbit the moon because they had so much propellant left on board. We've considered such an application as well.
Now, how do you monitor the use of the propulsion system? Obviously, you can't go refill MMS mid-mission. So what kind of monitoring system do you use to make sure you're where you need to be before that big move?
As you might know from whatever fluid dynamics classes or exposure you may have,
So this is the subject for today, fluid dynamics. This is a relatively simple topic.
There are really not a whole lot of parameters that we can measure in the propulsion system. The main one is pressure. We monitor the pressure of inside the tanks, and we also measure the temperature throughout the system. So if you know ideal gas law, you know that with pressure and temperature, as well as measurements of the volume of the system, we can characterize how much mass there is in the system at any time. We do have a blowdown system on MMS that is a non-regulated system. So the pressure decays with time as we expel the propellant. So knowledge of the pressure gives us direct knowledge of how much propellant and pressure and gas there is in the system. We need to know the performance of the thrusters, which we characterize ahead of time. It tells us the exit velocity coming out of the rockets, but we also need to know the mass of the system, both the dry mass and the wet mass of the system, so we can characterize how the spacecraft is going to move for any given maneuver, for any given amount of thrusters that we may fire at any time.
Is this something where you're just inputting data into a computer and the observatories are responding, or is there somebody with a joystick there like?
No, this is not a video game. This is not Star Wars where someone's sitting there, with a joystick flying a fighter. Yeah. No, how this typically works is that we'll send up a command through telemetry, which will get to each of the different spacecraft to tell them where they need to be. Mm-hmm. And then each spacecraft will respond accordingly to get into the position that they need to be in.
And how often would you have to make those kinds of communications to the MMS satellites during the flight?
It depends a little bit on what our orbital environment ends up being when we actually launch. But it's baseline that we would be doing orbit adjust maneuvers once every 2 weeks.
You mentioned a lot of factors that go into making that decision. How often do you get that kind of data?
We get that data almost on a continuous basis from the transponders and the low gain transponders, as well as the ground systems telling us where the spacecraft are. So we propagate the orbits with time, and that tells us when we will have to do a given maneuver. It's critical to the performance of the science that they all be within a certain range of parameters. So is distance as well as shape of the constellation. So the 4 spacecraft at any time form a tetrahedron. It's just a question of how good is the tetrahedron, how regular is the tetrahedron.
And so the burden on the propulsion system was to be able to allow the science team to make sure they could get in position to get that good science at the proper time.
That's absolutely correct, yes.
So Troy, you use models like this to actually help people understand MMS more thoroughly?
That's right, Blair. We find that many people are often overwhelmed with all of the details that you just saw, when you were in the clean room.
I'm still overwhelmed.
But models are one way, whether it be Lego, whether it be paper, whether it be balsa wood, or edible. We're coming up with all types of materials for people to learn how these models go together and a little bit more about MMS.
I'm insulted that you don't have an edible model here for me to learn with.
Where do you think we're headed right after here? Anything that we do that's actually hands-on and a lot of fun is just a way to bring people into the mission, so you can be part of the build of the mission, which is very unique. We're early on in the game with education this time.
Well, it's helpful, I can tell you that. I've noticed that inside you can sort of see the propulsion system that we talked about today, but I'm right. Afraid really to move too many parts.
Well, you might be able to. I'm not sure what will happen if you do. I used a little bit of super glue just because,
Now that's cheating.
That's cheating, I know. We'll work on a more solid system. But these models will all be available on the MMS website in the education section. Just awesome. Go to Education and Public Outreach for MMS.
Is there anything else there that they might get other than model building?
Well, along with the models, we have quite a few education guides that we're working on. One is a math guide for geometry. So it's on spatial geometry. And it also talks about the Atlas V rocket that the actual stack of 4 satellites will be inside of. When it launches.
Well, that's awesome.
Kids love rocketry, so that'll be a big part of this mission.
Kids and co-hosts.
And co-hosts.
love rocketry.
And their parents and their teachers.
Yes, exactly. Now, I understand that this particular model, or a similar one, was featured on the Big Bang Theory?
That's right. That really surprised us. We were able to send a constructed model to the producers, and every once in a while, they'll feature something like that on the shelf.
Well, maybe if you're good, NASA Edge will decide to feature the model on their set.
I don't know. That might be reaching for the stars. They're pretty hard to get through to sometimes.
Keep dreaming. Dream big.
We try hard,
You're watching NASA Edge, an inside and outside look at all things NASA.